Thank you very much, and I apologize for indeed slightly changing the title, although the content will not change by much. So I will talk about joint work with Yoshiko Ogata, and so it's also about quantum spin systems, as the talk by Robert. I think the main difference is that he had a system which has no spectral gap, or for which the spectral gap closes as you go to the thermodynamic limit, while I will be mostly interested in systems which have a spectral gap in the thermodynamic limit. And the other difference, I suppose, is that he was really interested in one particular model, and my aim here is a little bit different. It's rather to understand general features and giving a classification of these spin models, so really of families of spin models, instead of talking just about one model. So to start with, let me just introduce a little bit the formalism here. So Robert's Heisenberg model is, of course, an example of this, but this is, in a sense, general formalism. So I have a lattice, gamma. We'll think of ZD. In fact, in most of the talk, it's going to be in one dimension. It's just going to be Z. And at each point of my lattice, I have a finite dimensional quantum system of Hilbert space little hx, like here. And as long as I have a finite subsystem of my lattice, I'll call always lambda are going to be finite subsystems, and gamma are going to be the infinite systems. The Hilbert space is just a tensor product of the local Hilbert spaces at each point of x within lambda. So that's for the Hilbert space. The observables are just bounded operators on this, namely just matrices, right? All of these are finite dimensional Hilbert spaces, so these are just matrices, the dimension of which, however, grows with the size of the system. And the Hamiltonians, so I will, for this, before defining a Hamiltonian, I define an interaction. An interaction is essentially a map for which, so I can give a finite subsystem X of my lattice, and for each such little subset, I have a self-adjoint observable in there, which is localized. That means it's just localized in X, okay? And the Hamiltonian is simply the sum of these interactions, okay? So in Robert's talks, these were always 0, except for sets X, which are just two nearest neighbors. That would be a nearest neighbor interaction. I'll consider slightly more general things where this might have a finite range or even an infinite range, but in all cases I will have, in fact, to suppose that this decays fast enough in the size of X. And I will not go into the technical details. Essentially, think of exponentially decaying in the size of X. So I have a Hilbert space, I have the observables, I have a Hamiltonian, so of course I have a dynamics. So I'll think of the dynamics somehow in the Heisenberg picture always here. Namely, it's just the conjugating by the exponentials of that Hamiltonian. And you see, so I will always have this lambda, because that's only valid for finite systems. I haven't said anything so far about infinite systems. So what are states in this picture? Excuse me. So first of all, well, I had these observables on finite subsets. Of these things, I can take the limit to the infinite subset. I just take unions and then take the closure in norm, which means that an observable here is essentially always a limit, can be obtained as a limit of finite size observables. Okay, and a limit in the strongest possible sense, namely in the norm sense. Okay. You know, so typically things like the total energy of the system is not in there, but possibly the energy density might be in there. Okay. So states here, of course, in the finite systems, a state is just a vector. Precisely, in order to be able to talk about states in the infinite system, it's useful to think of them rather as expectation values of observables. And so for that, they're just positive, normalized linear functionals on the algebra. So in the finite volume, in fact, indeed, these are just density matrices. For each state, there's a density matrix. However, if you go to the infinite system, this is not necessarily the case. And so I will just have to talk about these functionals as such, not represented as density matrix. Okay, so these are states. So how do I think of the thermodynamic limit in this? Well, you can think of, so in the finite system, you have vectors in your Hilbert space that are, let's say, ground states. You can think of them as giving you expectation values. Okay, and of these objects, there's always nice limiting points as you let the side of the system grows. Okay, so there's always accumulation points of these objects, and this is how I will talk about the states in the infinite system. So always as limits of finite volume states. Okay, so not necessarily, there's other ways to talk about states in the thermodynamic limit, but I will keep to that definition. Good, so that's for the general formalism. Now, precisely as I said, I want to talk about kind of general families of quantum spin systems. And the keywords that goes with this in the literature is quantum phase transition. So, you know, the term quantum phase transition is a little bit misleading because in principle this has nothing to do with quantum. Really, it has to do, if you want to talk in vague terms, these are just phase transitions that happen as zero temperature. Okay, or another way of putting this, just as vaguely, is phase transitions that happened in the ground state and not in the thermal states. Okay, so here, to be a little bit more precise, so first I'll talk about quantum phase transitions for quantum spin systems. You could do that for other systems. And so here's the setting I will think about. So I told you about interactions out of which I construct my Hamiltonians. So I think of having a smooth family of such interactions. So I have a parameter that I will call S, which, you know, and I have a smooth family of interactions like this. Think of it as precisely an external magnetic field, for example, for a quantum spin system. So that would rather be an H, but I'll just talk about this. Now, for such interactions, you can define the associated smooth family of Hamiltonians, again, for any finite subsystem. And you can talk about the spectral gap above the ground state energy. So I told you I think of gapped systems. So, of course, for any finite system, this is just a matrix, so there's no problem to talk about the distance between the lowest eigenvalue and the next to it. That distance is just this gamma indexed by the size lambda and the parameter S. Okay? And so here's the kind of picture you have to have in mind. So this thing will be uniformly bounded in the size for all values of this magnetic field, S, if you want, this external parameter. So that's the first part here. But it might, this spectral gap, and that's really the spectral gap in the thermodynamic limit, if you want, would close at a particular value that I call the critical value of the parameter S. Okay, and it will potentially close with a given critical exponent, and that point, that's what's usually referred to as a quantum phase transition. Okay, so that's really where the spectral gap closes at a particular value of the parameter. Okay? So that's kind of the general setting. Now, usually associated to this, you have, even in finite system, if it closes, it can also close at the finite level, you'll have that the spectral projection, the ground state projection would also have some kind of singularity, would not be as regular as the map S to phi of S. Okay, so that's another type of definition you find of a quantum phase transition. But in a sense, before I start studying quantum phase transitions, one natural question is to ask, so what is even a quantum phase? Or, you know, again, I don't like this term quantum, but that's just the usual term. So what is a ground state phase? Okay, how would you define what you mean by a ground state phase? Vaguely spoken, that should be, you know, an equivalence class of models which have similar ground state properties. Okay, and I will try to understand essentially that first of all. Before this, I just wanted to make a little parenthesis about what's called sometimes stability. So you see, the first remark is, of course, the Hamiltonian as this sum of terms doesn't make any sense in the thermodynamic limit, because so that's essentially the Hamiltonian. If you look at this in norm, well, at least there's one term per site. Okay, so this norm grows at least as the volume of your system. So in norm, certainly, as I actually mentioned already before, there's no good limiting operator for the Hamiltonian. So how do you think of the thermodynamic limit? Well, in terms of not the Hamiltonian as an operator, but as a generator of the dynamics, okay? Namely as this object. And you see, as long as A here is an observable which is located in a finite volume, then this actually makes sense. You can take that limit. Okay, so that's kind of how you can talk about the dynamics, at least in the thermodynamic limit. Now, I've been talking about families of such Hamiltonians, so that would be such families. So I have two interactions, if you want, and I have a little parameter S between them. Okay, and psi would be of the same type of interaction as the phi. Now, as long as this psi is really a local thing, so it's not translation invariant, it's really just a little interaction that acts kind of strictly locally, so it's zero outside a finite volume, then, in fact, this S dependence is at least perturbatively always well understood. So, for example, you can understand the thermodynamic dynamics as a perturbation of the dynamics at S equals 0. You can convince yourself, you see that's, again, these are matrices, right? So that's just a finite rank perturbation. So if you have a spectral gap at S equals 0, you have a spectral gap, at least in a small neighborhood of S. You can convince yourself that if you have a ground state for the guy at S equals 0, then the Hamiltonian for the ground state for the Hamiltonians for small s is also just a local perturbation of the original ground state. I'm not saying these are completely trivial, but these are things that can be done, and where somehow the S dependence, at least perturbatively, is kind of under control. And you could, in fact, also do the same thing about thermal states. In that case, you have a nice continuous dependence of thermal states on these external parameter S. Now, precisely, usually, you're not interested in that kind of perturbation. Usually, you're interested in a perturbation which is really, truly translation invariant. So it lives everywhere on your lattice. Okay? For these things, essentially, there's no result about, or no general result about any of these points here. Okay? Because this perturbation, in a sense, is never small, because it always lives everywhere. Okay? And so, although there are some restricted results, there's no, that's usually called stability. And in particular, there's no result about the spectral gap, about the continuity of the spectral gap as a function of S. Okay? Good. Although this is precisely what I'm interested in. Okay? Good. So here's, you know, I've talked about this phase, so here's a definition that I essentially took from the physics literature. So it talks about Hamiltonians, not really about states. It talks about Hamiltonians, and it tells you that if you have two Hamiltonians, H and H prime, then you will say that they're in the same phase. If you have, you know, this is slightly simplified, but here's the gist of it. So if you can essentially interpolate between these two Hamiltonians in a way that the spectral gap doesn't close. So you see, I said before there's a phase transition wherever the spectral gap closes. So when are you not, or when are you in the same phase? Well, whenever you can find a path such that the spectral gap remains open. Okay, so that's essentially this definition. A little bit more precisely, so I have a path of such interactions that is continuous, piecewise differentiable, and that precisely interpolates between the interaction at 0, which is this one, and the interaction at 1 is the interaction for H prime. Okay, and so that's the interpolation, and the spectral gap condition is that, again, if you look at the spectral gap of the system at parameter S at the volume lambda, it's uniformly bounded in both S and lambda, and uniformly bounded away from 0. Okay, so the spectral gap just doesn't close. So that's a definition for two models being in the same phase. Okay? Now, just a notation, I will denote the set of ground states as S, this calligraphic S gamma at little s. So that's the set of ground states of the model defined at parameter S on the lattice gamma. And this dependence on gamma will in fact be important here. So you see, gamma, I said, that's the infinite sets, but I'm not necessarily only talking about the full thermodynamic limit. In fact, in one dimension, I will be more precise, let's also think of the two other possible gammas, namely the half-infinite chains with a boundary, because I will be interested in boundary effects. Okay? Now, one result that follows from this definition here, so you have here a definition involving Hamiltonians, and you expect that this implies something about these ground states. Okay? And so this is exactly what this theorem here tells you, namely if you have such a family here, then you can construct this alpha here, depending on the parameter s and gamma. So it's an automorphism of the algebra. And what does it do? Well, it takes the ground states of the system at parameter value s1, and it maps them to ground states of the system at parameter value s2. Okay? And this, not, you know, as a set of states, really. So it's really, this gives you a relation between the two sets of ground states. And precisely, you will be interested, or I will be interested, in models which have more than just one ground state in particular at the edges. Okay, so it will take the whole set of ground states of the system at S1, say on the half-infinite chain, to the whole set of ground states at S2 on the same half-infinite chain. Okay, so that's an important result following from the definition, which I think you should be happy about this because this talks only about Hamiltonians, but somehow when you think of you know, phases and phase transitions, it's rather about states. So that makes the connection between the two. Now this alpha, it's in fact a nice local. It's a nice local operation in a sense. That's what physicists use. Usually they say that these ground states are locally unitarily equivalent. So if you look at the finite system, this means that you have a unitary which is generated by a local Hamiltonian in a sense that generates this map. Okay? Good. Now, you see, that's a definition. And of course, if you want to be happy with this, you should find some invariance of these phases, some characteristic invariance of these phases, okay? Or it's just, in a sense, it's just a definition, okay? So in order to fill that with some physical and mathematical meaning. And so that's the question that I will try to address in one dimension, and in fact for a somewhat special class of Hamiltonians, called usually frustration-free Hamiltonians, and let me start by introducing them. So precisely, so now the lattice I have is just Z, so I'm in one dimension. And the Hilbert spaces, so at each point on my lattice, it's the same little finite dimensional Hilbert space, Cn. Okay, but n is just fixed for once, so it would be, you know, n could be 2s plus 1 if it's a spin S chain, right? So Robert had the case n equals, well, in fact, you talked mostly about n equals 2, but it could be anything. Okay? Now, so here's how we'll construct these Hamiltonians. So they're in fact constructed out of spaces, right? So I'll consider a family of spaces Gn that are subspaces of my chain of length n. That's this capital Gn. And I will assume that these spaces have the following property. I'll call that the intersection property for fairly obvious reasons, I guess. And so you see, what does that mean? That means that that space for a chain of length n is in fact completely described by the space, the equivalent space for the chain of a smaller length, namely little m. Okay? In a sense, you are in that space for the large n, if and only if you're in these spaces for all the smaller boxes of length little m that you can put inside the longer chain n. Okay? So I'll say that spaces, so subspaces of Hn of the Hilbert space of the chain of length n have the intersection property if they have that kind of property. So again, the space on the large, long chain is completely described by the equivalent space for the smaller chains. Why is this useful? Well, because in fact, starting from this, you can construct a very simple, there's a natural Hamiltonian for which these spaces are the ground states. And these are these frustration-free Hamiltonians. What do you do? Well, you define an interaction which is the following. You look at the projection onto G, so you fix little m. You look at the projection onto that space, or rather the projection orthogonal to it, right? And that's your interaction. It's just a translation invariant interaction, which is these orthogonal projection onto precisely the orthogonal space to this. So in particular, when you apply it to Gm, it's 0, right? But precisely by the intersection property, if you take a sum of 2 or 3, then in fact, the kernel of the Hamiltonian defined with that interaction on the chain of length n, well, it's just exactly going to be this Gn by this intersection property. And that's also where this term frustration-free comes from. It's essentially that you can minimize, you get the energy minimizer of the Hamiltonian on the long chain by really minimizing every single term locally of your Hamiltonian. Okay? That's exactly what I think that's a fairly understandable version of frustration freeness. This is not the only definition, by the way. That's the one I will take. Okay? So these are these frustration-free Hamiltonians in 1D. Now the question is, how do you actually get some of them? How do you construct such spaces, right? I started from spaces, but then I need to construct these spaces. And here's one way to do it. Okay? So so you remember n is the dimension of the spin, if you want. Huh? So I look at matrices. So I have an auxiliary matrix algebra of dimension k. These are the k by k matrices. And I look at vectors of length n of such k by k matrices. I will denote this by this b, well, that kind of b. I don't know how to know this. And I will need two projection p and q within these k by k matrices. So here are the two objects that will be central for the rest. So please try to remember what they are. So first, there's a completely positive map on that auxiliary matrix algebra. You see, so if I have such n such matrices, k by k matrices, I can construct a completely positive map out of them by just thinking of them as being the Krauss operator of that map. So it's the sum of the conjugation by these b's. So these b's are not unitary or anything, right? They are just arbitrary matrices. That always defines for you a completely positive map. Okay? So that's this E hat of B, because it depends on B, right? Now, this is just a notation. So this B is in this set B and K of PQ. So I will be interested in the spectral radius of this. This is a somewhat simple object. This is a finite dimensional, this is an operator acting on finite dimensional matrices, right? So the properties that I will want for this E hat is that the spectral radius is 1, and this 1 is a non-degenerate eigenvalue. I want the peripheral spectrum to be trivial. What is the peripheral spectrum for these completely positive maps? Well, you see, so 1 is an eigenvalue, but I could have other eigenvalues on the circle of on the unit circle, right? So I will need an E hat for which there are no other eigenvalues there. So there's really a spectral gap below the eigenvalue 1, in absolute value. And where do these two projections P and Q play a role? Well, they are essentially, you see, I can look at the eigenvector corresponding to 1, the left and the right eigenvectors. See, E hat is not self-adjoint or anything, right? It's not even normal. So the left and right eigenvectors are just E and B. These are my notation. And I will suppose that E and B are invertible on somehow P MP or Q MQ. So they are the subs. You see, they're always positive operators, but they might have a kernel. So P is essentially the orthogonal projection to the kernel of E, and Q yes, exactly, to the orthogonal space. So that's where somehow the subspaces of MK, where E is strictly positive and rho is strictly positive. Okay? So these are the objects. And the last one is precisely, you see, I'm interested in constructing spaces, so I will construct spaces with this map here. So again, so psi is just psi mu is an orthonormal basis of the on-site Hilbert space of Cn, right? So you see, I give you here a vector in the chain of length n, okay, that I expand in this the simple tensor product basis, and the coefficients are given by this. So to each value of the n tuple mu1 to mu n, where each mu goes from 1 to n, the coefficient is just given by this trace. So I have a product of these b's here, right? And in front I can put any operator I want in somehow P MQ. Okay? So I take an operator in MK, in my matrix in MK in my auxiliary algebra. I can construct these traces, and this gives me a vector in the Hilbert space of length n. Okay? So that's a construction so far. You see, so far it doesn't mean anything. I'm essentially telling you that in nice cases, the range of this is just going to be exactly good spaces for me. Okay? Good. So you see, just to so n here is the length. P and Q are these two projections. K is the dimension of the auxiliary algebra, and B are, well, the generating matrices. Okay? So these also go under the name of matrix product states for obvious reasons. Okay? In fact, they're slightly generalized because usually you don't have these P's and Q's, but they will play an essential role for me. You see, in particular, if E and B are really strictly positive, if E and rho are strictly positive, so the largest P and Q would be 1, of course. But you can still introduce, they're also invertible on smaller spaces, right? So that will be important for me. So here's the first little result. So if I denote by G the range of these gammas, and I construct on top of these, as I said, so I can construct an interaction which is the orthogonal projection orthogonal to these states here, then as long as these G's satisfy this intersection property, namely this Hamiltonian sense is well defined, then you can prove that this Hamiltonian has a spectral gap. So the spectral gap above the ground state energy remains open in the thermodynamic limit. There's a unique ground state on the full chain, okay, that I will denote by omega infinity b. But, and that's where, in fact, that's the important part here. You can also talk about the ground state spaces on the two possible half-infinite chains, namely, so this on the negative half-infinite chain and this on the positive half-infinite chain. And there, in fact, I can tune, precisely with these projections P and Q, I can tune the dimension of these edge spaces. Okay? And so in fact, these, let's take this one. So the ground state with a right edge is in fact, bijectively equivalent to the states of matrix algebra of dimension dl, namely the dimension of my projection P. And I can do the same on the right half-infinite chain. So you see, these Hamiltonians, they're all the same. So they have a unique ground state in thermodynamic limit, and they have ground state on the half-infinite chains. You have somehow Bloch spheres that sit at the two edges, and you can tune the dimension of these Bloch spheres. Okay, Bloch usually is for 1/2, but here precisely we can just tune the dimension by choosing the dimension of P and Q. So that's these Hamiltonians, and they are a generalization of the finitely correlated states, or parent Hamiltonians to those introduced by Nachtigall, Van and Weber. Good. So let me try to describe what is this bulk state, so this unique state in the thermodynamic limit, and how it's related to the objects I've introduced. So I had this E hat, so I can in fact extend a little bit this E by, instead of just looking at, oh, I put the star at the wrong place, it should be on the other side, it doesn't matter. So I have this E, which you see takes an observable at one site and a matrix in the auxiliary algebra, and it gives you, and you can, construct an object like this, and particularly if A was 1, this would be a delta mu nu, and you would recover the E hat I had before. And so that state is in fact constructed as the following. So if you want to compute the expectation value of such a product of observables between sites x and y. So I have this observable ax to a y on my chain, and I want to compute the expectation value of this. So how do I do this? So you see, I start somehow at the right end of my chain, and I put here E, which is the right eigenvector to E hat. And then I just act recursively somehow with this operator A, E indexed by the observable. And I construct this until I reach the last observable, and then at the left edge, I take the expectation value in that state rho. Okay, that's just a recipe. Okay? But you see that it has a very simple structure, right? They're also called quantum Markov chains for a somewhat obvious reason. You construct the whole state by starting at a point, and then you just go along your chain, and when you reach at the end, you take an expectation value. And you see all of this is somehow finite dimensional, right? These are all finite dimensional matrices. So they're all somewhat very simple states. Now, although it's not obvious to see, but you can convince yourself that, in particular, if you look at the expectation value of my interactions, then they're 0. So in fact, this is indeed a ground state on my chain. Okay, so that's these ground states. And why are they interesting? In particular, because they have exponential decay of correlations. And this is something that is fairly easy to see. Because you see, if I put just an observable at x, an observable in y, and nothing in the middle, it's just ones, and I apply this formula, so you see here in the middle, I'll just apply my e hat, which is e of 1, many, many times. Now, what did I assume for this operator e hat? That 1 is its unique eigenvalue. Sorry, so there's a non-degenerate eigenvalue at 1, and then a spectral gap below it. And so when I apply this, I'm just exponentially decaying by the distance between 1 and the first eigenvalue. So you see that somehow the exponential decay is directly related to the spectral gap condition on this E hat. And in fact, what the theorem tells you is that the spectral gap of E hat is also immediately related to the actual spectral gap of the Hamiltonian in the thermodynamic limit. Okay, not only exponential decay of correlations, but also the spectral gap of the full Hamiltonian. You see, this was the first statement here. Okay, so if this E hat has a spectral gap, then the Hamiltonian has a spectral gap. Good. Now for the edge states, well, I'm going maybe a little slower than expected, so I will not say much, but you see, instead of starting with E and finishing with rho, which are very specific eigenvectors of this matrix, I can choose, let's say, on the right edge, I start with the same E, but I can put another state here, right? I can put another state on the left edge, and if it's not the eigenstate for the eigenvalue 1 of E hat, then that will in fact give me a state which does not extend to the left, and it's really a boundary state. And in a sense, from this, you see that these edge states are parameterized by the states you can choose on MK. And therefore, you have this bijection between the states on MK and the actual state, the boundary states of my chain. But okay, let me not spend too much time. Because here's the essential theorem I wanted to present. Namely, for these Hamiltonians, so for these frustration-free Hamiltonians, I have a complete classification in the sense of the original definition of the phases. Okay? So if I give myself two such Hamiltonians, that I call H and H prime, so you see they're constructed out of matrices B's and B prime with projections that are also different, P, Q, and P prime, Q prime, all of these in principle of different dimensions, and even the dimension of the auxiliary algebra in which these auxiliary matrices live are of different dimensions. But so here's the statement that H and H prime are in the same phase with respect to that definition, if and only if these DL and DR, which parameterize the dimension of the edge states, the number of edge states, are equal. Okay? Namely, the dimension of these edge states are the complete invariance of my classification for this family of Hamiltonians in one dimension. Okay? That's the statement. So, in particular, if I give myself two such Hamiltonians, I'm able to construct a path of Hamiltonians interpolating between the two such that the spectral gap does not close along that path. Okay? That's in fact how the proof goes. You see, you could refine your classification by saying, I don't want any path of Hamiltonians. I want paths such that the interaction is symmetric under some symmetry group along the way. Okay? So that would give you a finer classification, of course, and I do not consider this here. Okay? That's why, in a sense, you see, it's a very, obviously this does not carry so much information, but it does carry some information. So the symmetries are not required here, and you could ask the same question by saying I have a symmetry group, I don't know, a symmetry group G acting and what is a classification. We have also some results on this, but it's a bit different. So as I said, the proof goes by just really constructing this path of interactions. And so here are a few remarks. So the chain is fixed. So I have really my little spins that sit there, and I don't change change this, because there were previous results in the physics literature where essentially they allow themselves to have ancilla. These are people from quantum information theory. So they have extra ancilla, and they can somehow increase the size of their spins. That makes the problem, in fact, much easier. Also, I have really a translation. I construct a translation invariant finite range interaction. In particular, I do not allow myself to not look at the spins as they are, but to look at them as blocks. So looking at them as blocks makes your spin dimension also larger, and that also makes the problem simpler. So I will not do this. So I really have these spins, and I really construct the path of interactions between these physical spins that actually sit there. And so one thing that goes with this is, in fact, we can also construct in each of these classes. So I have now these equivalence classes of Hamiltonians, and in each of them I can construct a very simple one. So here they are. In fact, I have a little restrictions on n. So what I'm saying is that for each integer dl dr, which are the dimension of these edge spaces, so k will be just the product of the two. I can give you a vector, an n vector of k by k matrices, and construct two projections p and q, such that the dimensions are correct. dl and dr are these edge space dimensions, that there should be the dimensions of the projections p and q. That's what they are. This B has the right properties in the sense that the E hat associated to it, the completely positive map for which these B's are the Krauss operators, has this spectral gap, and therefore the Hamiltonian is in fact gapped. And for those guys, I can actually prove that the intersection property holds, so these spaces are in fact spaces as I want them. But the whole point of this is that, so by the proposition before, we know that there's a unique ground state in the thermodynamic limit. What these states have in particular is that this unique ground state is the simplest possible state you can think of, namely a product state. So you see, if you look at the expectation value of a product of observables at each site, well, it's just given by the product of the expectation value in one given vector. Okay, so there's no correlation whatsoever. Okay, so that in fact gives you how weak somehow this classification is. So because in each of my models, the only invariants are the edge states, so how I see what I see when I cut the chain in two. And in fact, in each of these classes, there's one model for which the state on the whole line is just a product state. So where I can actually kind of erase all correlations. Okay? So that really gives you also an intuition of what this definition of a phase is. Okay, so I just wanted to mention that although these systems may look a little artificial, there's at least one which is halfway realistic, which fits into this classification. It's the AKLT model of Affleck, Kennedy, Lieb, and Tasaki, introduced in the 80s. So it's an SU2 invariant antiferromagnetic spin 1 chain. So it has a spectral gap, in fact. In fact, in that case, you can even give a numerical value for this spectral gap. So here's the interaction, so it's spin 1, right? So you see you have all possible SU2 invariant terms, the constant S.S and S.S square. With those parameters and these constants, in fact, make it so that it's in fact the sum of projections on the spin 2 subspace of the tensor product of two spin 1s. Okay? But you see, so when I write it like this, it looks like a bona fide essentially something like the Heisenberg model, the antiferromagnetic Heisenberg model. And when I write it like this, it suddenly looks like one of these models I introduced, where the interactions were just projections, right? That's exactly what I had before. And in fact, it is true that you can construct the ground states of those by this matrix product construction. And you know, here are the matrices. So you see the dimension of the auxiliary algebra is 2. And you can compute the left and right eigenvectors. They are in fact, they're essentially 1. So they are invertible on the whole algebra. That's why I have 1 and 1 here. And you can look at the ground state space on the two half-infinite chains, and they have essentially two spin 1/2s sitting at the two edges. So that means a two-dimensional space, so to say. So this, in fact, belongs to the phase 2 in my classification. Now, the important thing, in a sense, is that although it's not proved, it's expected that the KLT model is in the same phase as the antiferromagnetic Heisenberg model. Okay? So what would you need to do this, to prove this? Well, to construct a path and prove that the gap does not close. But this is hard, and this is not done. Okay. Good. So in the 10 minutes I have left, I'll give you a few words about the proof. You see, I think if you understand this slide, this is in a sense the most important part. So you have to remember the construction of these Hamiltonians. So where do you start? Well, you start from these matrices. You have these n matrices of dimension k. Out of these matrices, you construct these two operators, E hat and gamma. The E hat allows you to construct the state in the thermodynamic limit. The gamma gives you vectors that are in fact the ground state for the finite chain. Okay? So out of matrices, you have these things. The range of this gamma for finite chains, I called it G. These are the space, there will be the ground state spaces that satisfy the intersection property. And because of this, I can construct an interaction and therefore a Hamiltonian out of this. So that's kind of the line. You see, to construct a family of Hamiltonians, what do I need to do? I need to construct a path of such vectors of matrices. Okay, so that's somehow the philosophy, okay, of the proof. And you have, the nice thing about this is that you have, by the proposition I gave before, you have a control of the spectral gap of this by controlling the spectral gap of that operator on k by k matrices. So you have a very complicated problem a priori, namely a spectral gap of quantum spin chains, reduced to controlling a spectral gap for these completely positive maps, E hat. Okay? So that's really the idea. Let's construct a path of such Bs. Okay? Now, of course, you have to construct these Bs in the right way. I have lots of hypotheses, and that's where the problem lies. But so here's the summary of what I said. So if you start with two Bs to construct these Hamiltonians, they have, in principle, they're different in all possible parameters. So how will you construct a path of Hamiltonians? By interpolating somehow. You see, K is the dimension of these auxiliary matrices. So you can, of course, embed the smaller one to the bigger one. Well, you start by doing this. Then these projections, and that's where you already see that you need the same dimension for these projections. You want to interpolate between these projections. Well, so you can do this, of course, if the dimensions are equal. And then it remains, the harder part is to interpolate between these matrices B so that all conditions are satisfied. In particular, if you don't want the gap to close, you want to keep the spectral gap open also in these E hats. And that's the hard part of the problem, really. Okay? So really, the whole thing is related to proving that a certain subspace of vectors of k by k matrices is pathwise connected. Okay, at the end, that's the statement that needs to be proved. Because if I can construct such a path of matrices with the right properties, I can kind of automatically, by the previous proposition, construct a path of Hamiltonians. Good. Now, you know, I said completely positive maps. I talked about spectral gaps for completely positive maps. The natural thing that comes to mind is to use Perron-Frobenius, because that's exactly what Perron-Frobenius theory gives you. So I recall here the definition of this E hat. So the B's are Krauss operators for this E hat. What does Perron-Frobenius theory tell you? Well, it tells you that if it's an irreducible map, then indeed the spectral radius is non-degenerate, its corresponding eigenvector is strictly positive, and it tells you something about the peripheral spectrum. It's not empty in general, but you know something about it. And in fact, what's called a primitive map is the cases for which precisely the peripheral spectrum is empty. Now, luckily enough, you know, mathematicians knew this before, and there's a necessary and sufficient condition to have such a primitive map, which is expressed in terms of these Krauss operators, and here it is. So it tells you that there exists a fixed m such that monomials of length m generate the whole algebra mk. Okay? So the only thing that is hard here is that it's not all monomials up to m. You have to find one fixed m such that all monomials of length m generate all matrices. Okay? But that's the condition that we will use. Okay? To construct primitive maps, and primitive maps are exactly what we need to construct Hamiltonians, to construct gapped Hamiltonians. So here, you see, in fact, we even reduce this problem simpler by choosing a certain subspace to a problem of finding a path in C. Okay, we have to find a path in in Cn, but you have some surfaces in there that you're not allowed to cross. But you see, in Cn or in R2n, as long as the codimension of these surfaces is at least one, at least two, you can always go around it, right? In 3 dimension, you can always go around the line. So that's really what we're using here at the very end of the day. There's a lot of reduction to be done, but at the end of the day, that's what you do. And in algebraic geometry, apparently, it's called the transversality theorem. That tells you they can always do this. Okay, so out of this, really, so you construct this path of matrices that, so by Perron-Frobenius, they have a spectral gap, so you have a good E hat. On top of this, we can prove that the gamma, which gives me the ground state spaces, is injective. And you see it's defined on a subspace of matrices, which is P, MK, Q. So you see that the dimension is exactly dl, dr, namely, on a finite chain, the dimension is the product of the edge dimension on the right and the edge dimension on the left. So that's already what you want. You can prove that these G's constructed, the range of these are in fact do satisfy the intersection property. Therefore, you have a good path of Hamiltonians. Okay. So I think this is the essence of the proof. Precisely the range of the interaction, you can fix it essentially once and for all. You have to twiddle a little bit at the edges, the beginning of the end of the path, but there's a fixed, essentially, you don't have to take an interaction which is arbitrarily large because that would be nonsense. Okay. And what I've proved here is that if I've given dl and dr, so the edge dimensions, that I can find a path in between. So that's a sufficient part of the proof. The necessary is much more simple because I constructed this alpha, which is a map between these edge ground state spaces, and it's bijective, and therefore it has to conserve the dimension in particular. So the necessary part is essentially trivial. So I wanted to tell you about the concrete product representatives, but let me skip this. So here's what we've done. So we've constructed, first of all, gapped Hamiltonians that are frustration-free, so from this intersection property. They have the property of having a unique ground state in the thermodynamic limit, but for which we can kind of arbitrarily tune the edge state dimensions. And for those, we have a complete classification of this family of Hamiltonians in one dimension by really the number of edge states on both sides, which may be asymmetric. And again, I repeat, this is a classification which does not take symmetries into account. And the last point is that in each of these phases, I have one very specific representative, which is whose ground state in the thermodynamic limit is just a product state. Okay? Now, since this is all related to topological order and such questions, you could say that this shows that there is no bulk edge correspondence associated to this definition, right? Because in each phase where you can tune the edges, you have the same bulk state, so you don't see anything in the bulk. Okay, and that in fact may tell you that this is maybe not exactly the right definition, but so I will close, and then I think I'll have some questions from John Michele. Thank you very much.
Let's begin.